So last time we talked about cellular homology. So cellular homology is what you get when you have a cell complex and you want to take its cell complex structure into account to define a homology theory. So previously we had done this for delta complexes, and now we can do it for an arbitrary cell complex. So if X is a cell complex, where of course we mean that X is a topological space and we've chosen a cell complex structure on X, then we define a chain complex where the nth group is the free abelian group on the n cells of X. And the boundary map we showed after some work that what this does to an n cell in here, well, it necessarily gives you a combination of n minus 1 cells. And the coefficients are given by the degree of maps where you take the boundary of the n cell, you attach it onto your space X, and then you collapse everything except the n minus 1 cell you're looking at, so that you end up with a map between spheres of the same dimension. Such a thing has a degree, and that degree gives us this coefficient. So we actually started with, so alternately, you can write this in terms of the homology of the n skeleton relative to the n minus 1 skeleton, and then the boundary map is given by composing the connecting homomorphism in the long exact sequence of the pair, and then the inclusion map from a different long exact sequence of a pair. Right, and so whereas this one is easy to compute and very geometric, this definition is much easier to prove things with. In particular, showing that this is a chain complex, meaning that this squares to 0, is easy because when you compose this with the next one, you end up with 2 consecutive maps from the same long exact sequence, and so the composition has to be 0. Okay, so that was cell homology, and we used this to compute, for example, the homology of the surface of genus G, the orientable surface of genus G, and we saw that you get Z if n is equal to 0 or 2, and C to the 2G n is equal to 1 and 0 otherwise. Right. We also did the case of RPN, which will come back, so I want to talk about it again. So RPN is the quotient of the sphere when you identify every point with this antipodal point. So we notice that if you have the quotient map then you can view the, say, the upper hemisphere union RPn minus 1 is RPn. So the picture is that you have here Sn, the hemisphere is Sn minus 1, so the equator is Sn minus 1, the upper hemisphere is U, and when you take the quotient, well, you get the quotient map of U, and without any identifications, but Sn minus 1, the quotient of that gives you Rpn minus 1 because you're identifying antipodal points there. So the way to think about this is that Rpn is obtained from Rpn minus 1 by attaching an n cell. So this upper hemisphere is a disk, and all we have is an attaching map on its boundary, so an identification map on n cell by the quotient map. Okay, so.
Sorry, can you say again why it's Q of U union RPn minus 1?
Sure. Yeah, so if you look at the sphere, you get RPn by taking the quotient where you've identified every point with its antipodal point, right?
Yes.
So perfect. So if we take U to be the upper hemisphere, then we're not doing anything to points in U, right? Because from the sphere, they would have gotten identified with somebody in the lower hemisphere. So if we just take U, then this is it's not doing anything. It's just taking one copy of each of these points. You're only making identifications when you get down to the boundary, right? So you can think of RPn as taking Sn and making this identification, or of taking the disk and identifying points on its boundary.
Okay.
Right? So, yeah.
Which is what RPn minus 1 does.
Exactly. So making those identifications on the boundary gets you Rpn minus 1. And so you're really just attaching the disk to Rpn minus 1 by this quotient map, and you're getting Rpn.
Okay.
Right? So, yeah. But of course, Rpn minus 1, you could do the same thing with Rpn minus 2. And so inductively, Rpn is just one cell in every dimension until you get to n. Has a cell complex structure with one cell in each dimension until you get to n. Okay, so that means that the CW complex of Rpn is just Z for k less than or equal to n, and then 0. All right. And last time we computed the degrees of these delta maps, and we saw that the complex looks like each boundary map is multiplication by either 0 or 2, depending on parity. And so the complex looks like this, and the homology Z if k is equal to 0 or k is equal to n and odd, C mod 2z for k in between k odd and 0 else. Okay, So that's what we did last time. Any questions on last time? Okay. So I want to do another example where cellular homology is very easy to compute. So, and that's complex projective space. So just like real projective space, this you can think of as, for example, all one-dimensional complex subspaces of Cn plus 1, or by identifying each complex subspace with the unit vectors, you could think that you're just looking at the sphere where you're identifying a vector with another one if they differ by multiplication by a constant, and that constant has length 1. Right? So this is how we got the description of RPN as Sn mod out by the antipodal map. Right? RPN is defined to be all one-dimensional real subspaces of Rn plus 1. And what you do is you just identify each real line with where it intersects the sphere. And so you just get 2 points. So it's just a sphere where you identify each point with the antipodal point. So here you do the same thing, except you're working with complex subspaces. So that means that the unit ones, you have a whole circle's worth of unit vectors. But otherwise, you're doing the same thing. You're looking at the appropriate sphere, and you're identifying 2 vectors if they come from the same complex subspace, which means if they differ by multiplication by a unit complex number. Okay? So that's the space. And so to find a nice cell complex structure, we want to let's think about how we found this cell complex structure. We looked at the upper hemisphere, and we decided to use that as, say, the bulk. So one way of thinking about that is that every point on the sphere has its last coordinate is a real number, which varies between -1 and 1. But because you have this freedom of replacing a point with the antipodal point, you could always assume that the last coordinate was greater than or equal to 0. Right? And so that's what we ended up looking at. The upper hemispheres, the ones where they're strictly positive, and then its boundaries where they're equal to 0. So you can do the same thing here. Every class has a representative whose final coordinate, which is in principle a complex coordinate, is real and non-negative. Right? So if you give me any class here, it's an equivalence class of vectors where I'm free to multiply by any unit vector without changing the class. And so I can always look at the last coordinate and multiply it by the appropriate vector of unit length to get it non-negative. Right? If it's positive, then I have a unique representative. But if it's 0, then I can multiply by whatever I like, and nothing happens. So this is unique. This coordinate is non-zero. Okay, so these representatives look like some vector, and then the last coordinate is a real number, and it has to end up in the sphere. So this last one has to look like this. Right? So this would live in Cn squared. And this is the final complex coordinate, though it's actually real. And because we're on the sphere, this complex one is actually inside, has absolute value less than or equal to 1. So this is a graph. This is the graph of the function w goes to this over the disk. Let's call it d2n plus inside Cn. Well, over the disk. Right, so the space that you end up with is topologically, say, exactly the disk. You just have the disk, and you've pulled it up a little bit so that it's given you the graph of that function.
What do you mean over the disk? Or is that what you mean over the disk?
Yeah, so this omega is varying over the disk, and you're getting its graph, right? Because here omega has to be less than or equal to 1 for this to give us a point on the sphere. So it's just like now if you had the interval and you have the graph of a function over the interval, you could of course just push that down to the interval. So topologically, you just have the interval. Right? So same thing here. We just have the disk. We've pulled it up a little bit so that it looks like this graph. And so CPn is what you get from this disk by making identifications on its boundary. Right? So the boundary is precisely when the last coordinate is equal to 0. So the boundary to equivalence classes omega 0. And here we mod out and here we identify omega 0 with lambda omega 0 if lambda has unit length. Right, so this boundary is S2n minus 1, and we're modding out by omega identified with this if mod lambda is equal to 1. So this is just Cp n minus 1. Right, so the conclusion is just like RPn is obtained from RPn minus 1 by attaching an n cell, here CPn is obtained from Cp n minus 1 by attaching a 2n cell, right? Because this disk had dimension 2n. Right? So inductively, we have CPn is just a union of even dimensional cells until you get to 2n. Okay, so this means that the CW complex of CPn looks like z's and zeros. Right, so this would be degree 0, degree 1, degree 2, degree 2n, 2n minus 1, 2n minus 2, 2n minus 3, 2n minus 4. Right. So all of these cells occur in dimensions with no cells in the contiguous dimensions.
Say that again?
Yeah, every time there's a cell, there's no cell in a contiguous dimension. Right? If you move the dimension up or down by 1, there's no cell. So that means that the boundary map, I don't have to compute the degree of anything. The boundary map has to be 0. So, knowing that the cellular complex computes the singular homology means that the homology of CPn is really easy. It's Z if 0 is less than k less than 2n even and 0 else. Okay. Okay, so so that's cellular homology. So anytime you have a space and it admits a cell complex structure, you can use that cell complex structure to compute the homology, and it comes down to computing some degrees to know what the boundary maps are. And if you're in the situation of having a natural cell complex structure, then usually the degrees are computable by staring, and then you're all set. Okay. Wonderful. So the next application of homology we want to look at is the Euler characteristic. So we've defined this already. We said that when it makes sense, that is when the right-hand side makes sense, then the Euler characteristic is just given by the alternating sum of the ranks of the homology groups, where, let me remind you, that the rank of an abelian group, so if A then the rank of A is equal to L if A is isomorphic to C to the L plus T plus torsion. So anytime you have a finitely generated abelian group, then you know that it decomposes into a direct sum of copies of Z and then copies of cyclic groups, right? So things with torsion. So the rank is just the number of copies of Z that you have, right? So one thing we saw before about the rank, and one very useful way of thinking about it is that if we tensor with Q, and so if A is given by this, then A tensor with Q is just Q to the L. Right. So the rank of A is equal to the dimension as a Q vector space of a tensor with Q.
Barely covered tensors last term in algebra.
Okay. Okay.
Is it important to be able to think of it this way, or is the first way sufficient?
The first way is sufficient, but it is useful to be familiar with tensor products. So let me just remind you why this is true, for example. So if A and B are abelian groups, then the tensor product is what you get from the free abelian group on generated by all pairs once you mod out by two relations. So if you do the group operation in A, then that's allowed. And if you do the group operation in B, that is also fine. So for example, so I think the main source of confusion when you're teaching algebra is confusing the tensor product with just the Cartesian product. So for example, if you have Q to the L and you tensor it with Q to the L prime, what you get is Q to the L times L prime. So the dimensions multiply. Whereas if you do Q to the L times Q to the L prime, then you get Q L plus L prime. Right, so that I think is the main source of confusion. And from here you can see that you're just going to get as your basis elements just the product of a basis here with a basis here. And so that's why the dimension is going to be the product. Okay. In particular, so of course you can tensor things that are much more general than just abelian groups. But for abelian groups, it's really easy to describe because this is the only thing you have to mod out by. A key fact is that if you have n times, so you end up with an abelian group, and in an abelian group, it always makes sense to multiply by an integer, right? Because, for example, if I multiply by 2, that's just this plus this, right? So because I can always translate multiplication by an integer into performing the group operation on this however many times, it always makes sense to multiply. And the key thing with the tensor product is that I can put that n on whichever factor I like.
What does it mean to be tensoring the individual elements?
Yeah, so this is just what the elements of here. Elements of here are finite linear combinations of things like this.
Okay.
So this is just how we represent the equivalence class of A comma B in this quotient. Okay, so suppose I have an element A and A is torsion. So there exists a natural number such that n times A is equal to 0 in A. Right? Then A, tensor whatever you like, is 0 in a tensor Q for any rational number. because what I can do is I can take A tensor Q, and I can write this as A tensor n over n Q, and then I can take this n and move it over. Right? So when you tensor with Q, you're killing the torsion. Right? And then it's easy to see that if you have Z to the L tensor Q, you just get Q to the L. Z is the identity for tensoring abelian groups. Okay. So here is a nice fact. If you have a short exact sequence of abelian groups, then tensoring with Q does not mess that up. Alpha, beta, so this would be alpha tensor the identity and beta tensor the identity. This is still a short exact sequence, but now of Q vector spaces. So still of abelian groups, but very nice abelian groups. So this is not, so as I mentioned, you can take tensor products of much more general things. And if you do that, then it's not true in general that short exact sequences go to short exact sequences when you tensor. Usually what you mess up is injectiveness. But if you're tensoring with Q, nothing goes wrong. It's still exact. So since not everybody will be comfortable with tensor products, let's go ahead and check this. So let's say we want to show that this is injective. So assume that alpha tensor identity of some element, A tensor Q, is equal to 0. So this is, by definition, alpha of A tensor Q. Right? And if this is 0, then, well, it doesn't mean that this is 0 because I'm tensoring with the rationals. What it means is that this is torsion. Right? So this tells us that there exists an the natural such that n alpha A is equal to 0. But alpha is a homomorphism, so that's alpha of n times A equal to 0. And since alpha is injective, that tells us that n times A is equal to 0. So A is torsion. But as we just saw over here, if A is torsion and you tensor it with any rational number, you get 0. So this tells us that A tensor Q was 0. Right? And so alpha tensor the identity is injective. Right? Let's see that we have exactness at B tensor Q. So beta tensor the identity composed with alpha tensor the identity is equal to beta composed with alpha tensor the identity, and so that's equal to 0. So composition is definitely 0. So we just have to check. So that tells us that the image of alpha tensor the identity is contained in the kernel of beta tensor the identity. So we just need to check the opposite. So if if we have B tensor Q in the kernel of beta times the identity, then that's the same as saying that beta of B tensor Q is equal to 0, and that's the same as saying that there is some natural number such that n beta B is equal to 0. Okay, but then beta of NB is equal to 0, and by exactness, there is an A and A with alpha of A equal to NB. Right? Okay, so now notice that if I do alpha of A tensor Q over N, alpha times the identity, alpha tensor identity of this, I get alpha of A tensor Q over N, which is equal to NB tensor Q over N, which is B tensor Q. Right? So I have the other inclusion. And finally, that is surjective is trivial. Finally, given C tensor Q, there exists B and B, beta of B is equal to C, and beta tensor identity of B tensor Q is equal to C tensor Q. Okay, so tensoring with Q doesn't mess up exactness of short exact sequences. There's a term for that. You say that Q is flat over C. But anyway, that won't come up in this class, beyond Q. Okay, so what does that tell us? If X is a cell complex, or rather, if X has a cell complex structure, then let's say with finitely many cells, then the Euler characteristic of X is equal to the alternating sum of the number of K cells. Okay, so you can compute if you have a cell complex, you can compute the Euler characteristic before you've computed the homology. You can just look at the chain complex itself and compute the alternating sum of the ranks, and that will give you the Euler characteristic.
This is the second time this lecture I've seen you write k greater than or equal to 0.
Mm-hmm.
Is such a thing? Is anything we've talked about defined for k less than 0?
You could. We don't. Yeah, no, we're not doing anything with. We did have, when you look at the augmented singular chain complex, it does have a chain group in degree -1, but it doesn't have any homology in degree -1. So yeah, no, really, I just mean that I'm not putting any upper bound. Right, the upper bound will come because there are only finitely many cells. Yeah, so just sum over everything, and that's what we get. Okay, so why is this true? Well, we have let's call Z Ck equal to the kernel of delta K CW, and let's have Bk be the image of delta K plus 1 CW, so that we have two short exact sequences. On the one hand, let's go with the chain group is Ck sits inside the chain complex, the kth group, and the quotient is the image of the next one, so Bk minus 1. And on the other hand, the homology is what you get by putting Bk inside Zk and taking the quotient. Right, so you have those two sequences.
Okay, we're just finding their sequences at this point?
Oh, they're short exact sequences. Yeah. Yeah, but so this is just because the first isomorphism theorem of group theory, right? The image is isomorphic to the domain mod out by the kernel, right? And this one is just the definition of Hk is Zk divided by Bk. Okay, but for any short exact sequence, the exactness of tensoring with Q implies that the dimension of B tensor Q is equal to the dimension of A tensor Q plus the dimension of C tensor Q. Which, if you like, is the rank nullity theorem. But, I mean, it's just, it is the rank nullity theorem. But anyways, this is easy to see. Right. There you go. Yes. Every short exact sequence of vector spaces splits. So you can always pick a map that goes back by just taking a basis here and mapping it to any preimage you like, and then extending linearly. So, and as we saw on a homework problem, I think, if you have a split short exact sequence, then the group in the center is isomorphic to the direct product of the two on the extreme. So, but however you like, the dimensions add. But of course, the dimension after tensoring with Q is the rank. So this says that the rank of B is equal to the rank of A plus the rank of C. So if we go back to those short exact sequences, we see that the rank of this of X is equal to the rank of Zk plus the rank of Bk minus 1, whereas the rank of Hk is equal to the rank of Zk minus the rank of Bk. So now multiply by minus 1 to the k and add.
get what?
Oh, to get the Euler characteristic of this complex and the Euler characteristic of this complex, right? But you're going to get the same thing because this shifted by 1 and the sign changed. And so when you do this, you're going to get the exact same thing. So, so to get that the Euler characteristic of x, which is the alternating sum of the ranks of the HKCW, is equal to the alternating sum of the ranks of the chain. Right? But the rank of the chain group is just the number of K cells. Okay, so that ties in with the Euler characteristic the way you might have seen it in a previous class or in graph theory, where you have a polyhedron, say, and you look at the number of vertices minus the number of edges plus the number of faces, right? So that's what you would get from the CW complex, right? And this says that, well, that's the same thing that you get by looking at the homology, right? And so if you're looking at a polyhedron, it's always the sphere, and so you're always going to get the Euler characteristic of the sphere. Speaking of which, we have, for example, computed the homology of the surface of genus G, and so you get 2 minus 2G. So you can think of that as saying that if you were to make a polyhedron with 2 holes, orientable, then the number of vertices minus the number of edges plus the number of faces would have to be 2 minus 2G, no matter what you did. Right? We also computed, well, we know the homology of the sphere, and so you're going to get 0 if n is odd, and 2 if n is even, right? Because for the sphere, we know the homology is just a z in degree n and a z in degree 0. And since you're alternating signs, they either cancel or add. We've computed RPN. And you get 0 if n is odd, and 1 if n is even. Right? Because the ranks, well, all of the C mod 2z's don't enter into it. All of those have rank 0. So it's just the set in degree 0, and you may or may not have a set in top degree. And CPn is equal to, what, 2 times 2n? So it's, no, 1 times 2n, 2n. So we computed this, and it has just 1 z in every even degree, right? So since it's even degree, all of the signs are plus, and each set just contributes 1. So you just add 1 to itself 2n times. Okay. Okay, so we can use this Euler characteristic of the surface to pay off a debt from earlier in the semester when we talked about covers, because a nice fact about the Euler characteristic is that it plays very well with taking covers. So here, I'll just sketch this. But if you have a covering map, and what else is, and the covering degree is finite, covering degree n, say, then the Euler characteristic of x is equal to n times the Euler characteristic of y. And the proof is just that you can pull back the cell complex structure of y to a cell complex structure of x, where every cell lifts to n different cells. Right? So, you know, if you have let's say you had the circle covering the circle by the map C goes to C cubed. And if you were to put, say, a couple of different vertices here and paths between them, then this is going to wrap around 3 times. So you would get, so let's see. So if you divide this in 3, you're going to have, say, this path is curly. So you'd have the curly path here, and then from here to there, curly path there, and here to there, curly path there. Right. So this is a 3 cover, and the 2 0 cells lift to 6 0 cells. The 2 1 cells lift to 6 1 cells.
Okay. When we say covering degree, that doesn't have anything to do with degree. It means the normal covering.
Right. Covering with n sheets.
Right. Okay.
Uh-huh. Yes, thanks. So, completely different use of degree. Okay, so what we did earlier in the semester, when we were talking about group actions and how those gave you covering spaces, we drew a picture like this. So we had a pentagon, and then in the center we're going to put a hole, and then we're going to draw like a star. And then on each leg of the star we put 2 holes. And this, right, with the pentagon just for drawing, this is a cover of the surface with 3 holes. So this was M11 covering M3. Right, hopefully that rings a bell. And we pointed out that you could have nm plus 1 and covering n, say, either one of them plus 1. right? And then what I said was that if you have a cover of a surface by another surface, then the genera have to be related like this, right? And so now we can prove that. So note, if mg over mh is a cover, then the Euler characteristic of mh has to divide the Euler characteristic of mg, right? Well, that's the same as saying that 2 minus 2h has to divide 2 minus 2g, and that's the same as saying that h minus 1 divides g minus 1. So if you have g minus 1 equal to nm, or let's say if h minus 1, so if h minus 1 is equal to m, then g is equal to some multiple, say n, times m plus 1. Right? So, so only a surface like this can cover a surface like this. Okay. Another cute fact. So we used the degree of a map to show that if G acts on Sn freely with n even, then G is a subgroup of C mod 2Z. All right, so we proved that using the degree of a map. Here's a quick proof. So alternate proof. Sn to Sn where did I put mod m? The orbit space is a G cover. So 2, which is the Euler characteristic of Sn, has to be equal to this times, call that m, call it chi of m. Wonderful. So the size of G has to divide 2. Of course, this works modulo justifying that M has a cell complex structure. Okay. Great. So that's what we want to say about the Euler characteristic for the moment.
About the last one, is there any particular reason we should believe that such an M does have? Are there cases where it's clear or not clear that it does or does not have a cell complex structure?
It really depends on what you assume about how the group is group acts. So if the group acts smoothly, so let's say you have a smooth manifold and you have a smooth group acting smoothly, then things can't be too bad. The quotient space will not necessarily be a smooth manifold. It can be pretty bad. It can be what's called a stratified space. But among stratified spaces, it is the nicest kind. So even though it can have singularities that look like the worst thing looks like a cone over a space that itself has singularities that look like the cone over a space that itself has singularities that itself look like, and so on. So it's just an iterated conic singularity. But those things do have cell complex structures. So as long as you started out with everything smooth, then there's no problem. Well, there's work to do, but you do end up with a cell complex structure on the orbit space. However, if you don't demand that things act smoothly, then even with finite groups, you can cook up settings where the quotient space is not a stratified space of that sort. It's called a Tom Mather stratified space or a Whitney stratified space. You end up with things that are called Quinn stratified spaces. So this is, anyway, it's a homotopically stratified space as opposed to a smoothly stratified space. And so it's much worse. But if things are smooth to start with, then there's no problem justifying a cell complex structure.
Define what it means for a manifold to be smooth. What does it mean for a group to act smoothly on it?
Right. So if a group is smooth, so for example, if you have a Lie group, then each element of the group is now just acting on the manifold, but it's just a map from the manifold to itself. So it makes sense to ask that that be smooth. So that's what it means to act smoothly. Okay. Okay, so next, the next application of the properties of homology we've established is what's called the Mayer-Vietoris sequence. So this is analogous to the Seifert-Bank-Kampen sequence for the fundamental group. Right? So this is Mayer-Vietoris. Okay, so these are two Austrian mathematicians. They proved this in the late 1920s. Walter Mayer, had been a student of Vietoris, and Vietoris had mentioned this as a problem in the lectures, and Mayer was able to solve it in a couple cases, and then Vietoris was able to solve it in general. Mayer went on to work as an assistant of Einstein. He was known as Einstein's calculator. And when Einstein came to the US, Mayer came with him and was at the IAS. Vietoris was a little younger than Mayer, but still had served in the armed forces of Austria in World War I. And he did not die until 2002, at 110. His last published article was when he was 103 years old, was written when he was 103 years old, on a Fourier series. In fact, half of his papers were written after the age of 70. Okay, but here's what the Mayer-Vietoris sequence says. Say you have X, and you write it as the union of two spaces. In fact, the union of the interiors. Then there is a long exact sequence where you have the homology of X mapping to the +1, the homology of the intersection, then the sum of the homologies and then the homology of X. Okay, so I'll define the maps in a second. Okay, so this is really an immediate consequence of excision. You can prove it directly after excision with the diagram chase. But at this point, it's really quick to prove because, because this is induced by a short exact sequence of complexes. So take the sequence, so the singular simplices in the intersection, map this to the sum by taking the inclusions, and let's say you change the sign here. So I'm going to take the inclusion into A and then minus the inclusion into B. And then here, I'm just going to sum the inclusions into X, but I'm going to have to use this, this guy. So these are the chains. So here U is this cover. And if you recall, this stands for the free abelian group on the singular simplices that have image contained in one of the open sets. Right, so this came up when we proved excision. We proved that for any open cover, you get the same homology by looking at these simplices. Okay, so there is a choice of sign. You want this composition to be 0. And so here you're going to take a single class, and you're going to view it as a class in A, and you're going to view it as a class in B, and then you're going to put those two classes together. So in order for things to cancel, there has to be a minus sign somewhere. But it makes no difference whether you put the minus sign here, whether you take the difference and leave both of these positive, or whether you put a minus sign here and take the sum here. All that matters is that the signs work out so that the composition is 0. Okay, so we should justify that this is exact. This is injective because each of these is injective. This is surjective because we proved back when we did excision that it's surjective. So it's just a matter of showing that it's exact in the center. We already talked about how the composition is 0. So really the only thing we have to check is that if you have something in the kernel let's assume this is in the kernel, and we want to see that it comes from the image. So, so this tells us that A plus B is 0 in X, but that tells us that A is equal to minus B. So if A is equal to minus B, then A, which lives in C star A, also lives in C star B. And B, which lives in C star B, also lives in C star A. So that means that actually A and B are chains contained in the intersection of A and B. And so A comma B is just this map I A star minus I B star of A applied to A, because that's the same as minus B. So that gives us exactness. So that tells us there is a long exact sequence, and it tells us what these maps are. They're just the induced maps from here. we can be explicit about what the connecting homomorphism is. So the connecting homomorphism would go from Hn plus 1 of x to Hn of the intersection. And here's how it works. Given a class in here, we can represent it as a sum with u in C star A and v in C star B. Right, so this is something we proved when we were proving excision. This was barycentric subdivision. So we proved that you could do enough barycentric subdivision so that you ended up with a sum with each element having image in one of the open sets in your cover. So you can represent it as this. And since it is representing a homology class, we know that d of u plus v is 0. Right? But again, this tells us that d of u is equal to minus d of v. And since this is a chain in A and this is a chain in B, both of these are chains in A intersect B. So the boundary map, the connecting homomorphism, is just take the class of this boundary.
Which is the same as if we had v instead.
That's right. Up to a sign which wouldn't make any difference. So that is the connecting homomorphism. So a couple remarks. It's clearly enough X written as a union where A and B are deformation retracts of open neighborhoods. In X, that retract, so let's give them a name, say U and V, as long as U intersect V deformation retracts onto A intersect B. Right. So, so the theorem also, the long exact sequence also holds if you have this. So I don't need to have their interiors be the open cover, as long as I could thicken them up so that the interiors were the open cover. Right. Another remark is that you can use homology or reduced homology. Right. By which I mean that if you just put tildes on top of everything, it's still a long exact sequence. And you prove that by using the short exact sequence of complex augmented singular complexes. Okay, so for example, take the sphere and write it as the upper hemisphere union the lower hemisphere. Right. So these are closed sets, which is why we have this sort of remark, so that I don't need to bother thickening them up. So let's see what this says in that case. So then Mayer-Vietoris has Hn of hk of u plus hk of L maps to hk of x, which is Sn, maps to hk minus 1 of the intersection which maps to h k minus 1 of u plus hk minus 1 of L. Let's go ahead and put tildes on things. Okay, and u and L are contractible. So because I put the tildes, this is just 0, and this is always 0. And so we get isomorphisms between these. And of course, the intersection is just the equator, which is Sn minus 1. So this gives us yet another way of proving that hk tilde of Sn is isomorphic to hk minus 1 tilde of Sn minus 1. Okay. And we'll stop there.